Hi everyone, this is the course ISO657A. The course instructor is Professor Mark Crowley. I am Benyamin Ghojogh, the TA and presenter of slides. This is a lecture on t-Stochastic neighbor embedding, or t-SNE or t-SNE. First, I show some dataset notations to you. Assume we have a training data set. Each data point is denoted by xi, which is d-dimensional, and we assume that we have n data points. We consider the vectors to be column vectors, and we put vectors in matrices column-wise. So if we put vectors in matrix capital X, we'll have the data set which is d by n. We want to find the embedding of training data, which is denoted by yi. The embedding of xi is denoted by yi. Assume that the dimensionality of embedding space is h, denoted by h, and we have n data points. We don't in other lectures we had shown the dimensionality of subspace by p, but here we show it by h because we use p for the purpose of another notation in this lecture. And y, we put them column wise. If we put the embeddings column wise in the matrix capital Y, we'll have a matrix h by n. Usually h is less than or equal to d, and usually h is much less than d. In SNE and t-SNE, these are usually used for data visualization in either 2D or 3D, therefore h is usually 2 or 3. Okay. Do you remember we have in k-nearest neighbor graph, we say that either a point is a neighbor of another point or it's not. It's either so every point accepts another point either as its neighbor or not. So it's hard decision. However, let's make it a soft decision. Let's not say that you are my neighbor and you are not. Every point can say that you are my neighbor with high probability, but you are my neighbor with low probability. So every point is the neighbor of every other point, but with different probabilities. And what determines this probability? If 2 points are close to each other, we can say that those 2 points are neighbor of each other with high probability. But if they are far away from each other in the input space, we say that they are neighbor but with a very low probability. So every point can have a Gaussian distribution around it, where it itself stands in the mean of Gaussian distribution. And it says that using this Gaussian distribution, I can find out the probability of other points to be my neighbor. So if a point is very close to me, so it is close to the mean of this Gaussian, therefore it is my neighbor with high probability. But if it is very far away from me, it's a neighbor with low probability. I'm showing this in this figure. So assume that this point is in the middle of this, is the mean of this Gaussian distribution, and the point which is close to it is a neighbor with high probability, but the point which is far away from it is neighbor with very low probability. Therefore we can have a distribution, not necessarily just Gaussian, a distribution around every point to determine other points as its neighbors, stochastically, not deterministically. Okay, so we can say that similar points or close points are neighbors with high probability, dissimilar points or far away points are neighbors with low probability. This is a probabilistic approach for embedding. And SNE, a stochastic neighbor embedding, not t-SNE. SNE. t-SNE is a developed version of SNE. SNE uses Gaussian distribution for probability of neighborhood. Okay, I explain SNE here in this slide. So this is FD, this FD. This is the definition of Gaussian distribution, univariate Gaussian distribution. Consider this, and then you can see that this part is a constant. Therefore, if we drop this, this is proportional to this exponential term. Usually, people use, in machine learning you see it a lot, people use this formula as the probability for determining or for showing some kind of probability, and usually Gaussian distribution. This is called softmax function. And what is this? It says that I use this term of Gaussian distribution, which is the exponential term, but as we don't have we have dropped the constant here, this is not a PDF anymore, a probability density function. It doesn't sum to 1, or it doesn't integrate to 1 when we drop the constant. So in order to make it like a probability, make its behavior similar to probability and make it sum to 1 or integrate to 1, we divide it by all summation of all different cases. Therefore, when we sum all different cases, here we sum over I and j over all different points, pairs of points, the numerator becomes equal to the denominator, and the summation of total is 1. So we do this trick by dividing to the summation of all different cases. We are making this exponential term, which was proportional to the Gaussian distribution, similar to a probability distribution, and we use this as kind of a Gaussian distribution, and we set it to Pij. So the probability that the xi takes xj as its neighbor, it's a scalar also. This probability is a scalar. The probability that xi takes xj as its neighbor is equal to this Gaussian distribution, this softmax form. It is noteworthy that softmax has a problem. What is the problem with softmax in machine learning? The problem is that we have a summation in the denominator. What if we have the number of cases, or the number of points here is huge? What if the summation is over a huge number of cases? Then this denominator becomes interactable. So the softmax problem is prone to be interactable. This is the problem with softmax in machine learning. And here we are using Euclidean distance here in dij squared. We are using exactly what we had in the term of exponential term for Gaussian distribution. Squared Euclidean distance over the variance, two variance. This is used in the softmax form. And this variance is which we consider for the Gaussian distribution for xi, and it can be found by a binary search to find to make the entropy of distribution some specific value. What was the entropy of a distribution? The entropy I showed. This is the definition of entropy from Wikipedia, and as you can see that we have minus summation of p log p, and so what was p here in our case? P is equation 5, and so we can have we can say that I want the entropy distribution to be a specific value, and using binary search I can easily find what sigma I want to have, or we can just fix it to a fixed number. This is according to the paper of SNE, this technique. And then Qij is the probability that the embedding of xi takes embedding of xj as neighbor, or in other words, the probability that yi takes yj as its neighbor. We show it by Qij, so it's a corresponding variable for Pij, but in the embedding space. We also use a softmax or a Gaussian distribution, but we also have equation 8 is very similar to equation 6, but we don't have sigma I. Why? Because it's based on us how to choose the embedding. In equation 6 we used variance because we didn't choose the embedding. We already had we were given the data points. but in equation 8 we want to find the embedding points, so we don't care about those variances. So we use this squared Euclidean distance in the softmax form in order to have equation 7 as the Gaussian distribution for taking neighbors in the embedding space. Now we are going to use this. So what is the idea? The idea of SNE is that let's make these two distributions of Pij and Qij similar. I want I want that every point takes other points as its neighbors with a similar distribution as it had in the input space. So let's make Pi similar to Qi. And what is we have different distances, or we have different differences measures for distributions. One of them is KL divergence. KL divergence is defined as this. Here you can see the definition of KL divergence. So we have summation of j1 to n Pij log of Pij over Qij. This is it's very closely related to entropy as well. We have different other measures for difference of distributions. For example, one of them is maximum mean discrepancy, MMD. You can go and search about them yourself. One of them, the most famous one, is KL divergence. So let's minimize this KL divergence. Why? Because when KL divergence is 0, these two distributions are exactly the same. When they are different, the more different they are, the more different their moments. The moments of these distributions are, the more KL we have. And this we are summing over all n data points. So this is C1, we call it C1, and this is a scalar also. And we take derivative of a C1 with respect to yi. Yi is a vector, so is the embedding of xi is a vector which is h-dimensional. So this derivative is also h-dimensional. And why? I had said that in previous lectures, but I say this briefly too. The derivative of a scalar with respect to another scalar is a scalar, because when you tweak the second scalar, the first scalar changes. So this is interpretation of derivative. The derivative of a scalar with respect to a vector is a vector, because when you tweak the elements of the vector, it changes that scalar. The derivative of a scalar with respect to a matrix is a matrix, because by tweaking every element of the matrix, that scalar changes. The derivative of a scalar with respect to derivative of a vector with respect to a vector is a matrix, because every element of the second vector that we tweak, it changes every element of the first vector. The derivative of vector with respect to matrix is a 3 tensor. Why? Because every element of the matrix we tweak, it changes every element of that vector. So here we have derivative of C1, which is a scalar with respect to a vector, so it's a vector. And this derivative is this. Derivative of equation 9 is 10. For derivation of this gradient, see our tutorial paper on SNE and t-SNE. We can solve this equation. We want to minimize this C1. You might say, okay, one solution is that take derivative and set it to 0. But when we take derivative and set it to 0, we have yi and yj here, so we cannot have a closed form solution. What do? We can easily use gradient descent, for example. What is gradient descent? Gradient descent says that I find the gradient, and in the direction of in the opposite direction of gradient, I move, and gradually, iteratively, I move towards the minimum of the cost function. So this is what we have in gradient descent. But here we are using also momentum term. The momentum says that in order to have less oscillations in gradient descent, let's have some history from the previous steps. So if we usually, if this is a convex cost function, for example, sometimes when we don't use momentum, this is like the oscillations of gradient descent. But if we use momentum, the oscillation is less. This is the effect of momentum, the method of momentum. SNE uses momentum in gradient descent. So equation 11 and 12 is gradient descent with momentum. And this is the momentum parameter that they use. They also add jitter to the solution of initial iterations for better convergence of embedding. What is jitter? They just add some noise to so when they update for every iteration of gradient descent, after every iteration they add some noise. This helps the points to move better in order to converge faster. But after some time they don't do it. They don't add jitter. After some iterations they don't do it. They do it in initial iterations. Now there is also symmetric SNE, which was proposed in the paper of t-SNE. It says that, do you remember we had this in SNE? Here we had in equation 5. And consider this. We are summing over all points which are not I. Therefore, Pij in this case is not equal to Pji. Because for Pji we will have summation of k not equal to j. This makes the SNE not symmetric. In order to make it symmetric, we can say that let's sum over all pairs of points. Consider this, notice this. They replace this Pij with this, and this becomes a symmetric SNE, and they use the same Dij. But notice one thing. This Pij, if we use this squared one, this boxed equation, if we use this, it has a problem with outliers. Why? If point xi is an outlier, its Pij will be extremely small, because the denominator is fixed. You see that the denominator is fixed for all data points because it's summing over all pairs. Numerator will be small for outlier. If we have an outlier, it is far away from other points, much far away. Therefore, this Dij is huge, becomes huge, and exponential of minus Dij becomes very small. However, if we use the second Pij, this one, then the denominator for all points is not the same. Therefore, the problem of outlier is cancelled out. So still we have, by making this symmetric, we are causing a problem with outliers. So let's use another formula. Let's use the same Pij. We denote it with this. It means that let's take the probability that xi takes xj as its neighbor. But we say that we want Pij to be average of Pij plus Pji. We'll also normalize it by n. So in this way it has become symmetric, but we don't have the problem with outliers. So we use this equation 16 and 17 for symmetric SNE. We are repeating it here. But the problem, this problem that I explained for outliers, does not exist in the embedding space. Why? Because we are initializing the points and we are moving the points in the embedding space. We are choosing what points to be in the embedding space. We are not given the points. Therefore, we don't have outliers there. Therefore, we can use what we explained here in the boxed equation in the embedding space without having any problems. And so SNE uses equations 16 and 17 for the input space, and equation 20, this boxed equation, and 21 for the embedding space. And again we have C2, K divergence between Pi and Qi, but the difference is that Pi and Qi, the formulas for Pi and Qi are different, and because of that difference the derivative is also different. Compare this with this derivative. Because of having symmetry, this is simplified and we will have this. and we'll have 4 rather than 2. For derivation, you can see our tutorial paper. As before, we use gradient descent with momentum. In symmetric SNE, we also add jitter, like in SNE. Now, let's move on to t-SNE. First, t-SNE said that there is a problem with SNE, and that problem is named crowding problem. What is the problem? I'll tell you. Assume that in this you have 1 million people. Assume that you have 1 million people and you want to fit them in a room, in a classroom. How do you do that? Of course, 1 million people do not fit in just a classroom. What is the solution in order to be able to fit as many people as from these 1 million people as you can in this room? One way is to enlarge the room. The solution is simple. If you enlarge the room becomes larger, then you can fit more people. So in other words, in our case, when we are in high dimensional space, the high dimensional data has huge information. Information is corresponding to people in my example. And you want to include as much information as you have in the high dimensional space in the low dimensional space. But low dimensional space does not have enough number of dimensions. Or in other words, in my example, the room is small. What do we do in order to preserve the information of high dimensional data in the embedding space better? Of course, you will lose some information, but what do we do to make it better? Let's use student-t distribution rather than Gaussian distribution. A student-t distribution in terms of its shape, it's very similar to Gaussian distribution, but it has heavier tails. You can see it goes to 0 later, but Gaussian goes to 0 sooner. So it has heavier tails, and you can see that because of this student-t distribution is somehow enlarging the distribution. So as we had enlarged the room in order to fit more people, we are enlarging the distribution in order to have more to preserve more information in the embedded space. So let's use a student-t distribution rather than Gaussian distribution in the embedded space. Why? Because we enlarged the room, and the room was corresponding to the low dimensional space, which was the embedded space. But in the original space, we can use Gaussian. So in the input or original space, we use Gaussian, but in the embedded space, we use a student-t distribution. t-SNE does that exactly as before. It uses Gaussian distribution, but symmetric Gaussian distributions. Symmetric Gaussian distributions that we explained for the input space, these 3 equations, but it uses a student-t distribution, which is equation 26, with the same Zij that we had before. But this is a student-t distribution with degree of freedom 1. The student-t distribution with degree of freedom 1 with 1 degree of freedom is equivalent to the Cauchy distribution. A standard Cauchy distribution, which is this. It can, if you search, you can find its a proof in the internet why these are equal. A student-t distribution with 1 degree of freedom, and you can see that we are using this here. So we can say that original t-SNE uses Cauchy distribution, and so it can be named Cauchy SNE rather than t-SNE, the original one. And why is it why you might say, why are we using equation 28 here? Because if you say this term is in the denominator, when it comes to the numerator, we'll have power -1 as we have here. Also, using the softmax form, we are summing over all cases in order to sum to 1, in order to make the behavior like a distribution. So we again have C3 as a KL divergence between P and Q, similar as before, but P and Q are different now. So the difference is in P and Q. Because of this difference, the derivative is also different. you can see our tutorial for the proof. As before, optimization is done using gradient descent with momentum. But here in t-SNE there is no need to add jitter to initial solutions because t-SNE is more robust than SNE. They have empirically seen that there is no need to jitter. There is also something named early exaggeration in t-SNE. In t-SNE it is better to multiply all Pij's by a constant, for example 4, in the initial iterations. So they do this. You might say, okay, if we do that, Pij will not be a probability anymore because it won't sum to 1. It will sum to 4. That's okay. That's okay. It's a heuristic technique that they do that. And why do they do that? They call it early exaggeration. This heuristic helps the optimization to focus on large Pij's. So the close points, neighbors. When the points are close to each other, their Pij is huge. Am I right? And if you multiply it by multiply all Pij's by 4, the larger Pij's are exaggerated more than the small Pij's because of the characteristic of multiplication. Therefore, we want to take care of neighbors or similar points more in the initial points, and then in later iterations in the initial iterations. But in the later iterations, we say, okay, let's now also focus to far away points. So in the initial iterations of gradient descent, let's focus on the points which are much close to each other, which are similar to each other. Let's embed them close to each other in the embedding space. But in the later iterations, now we will start to care more about the far away points. This might remind you of what we had in local fitting. So it says that let's have local fitting in initial iterations. Later we will care about global fitting too. We had local fitting in LLE too. As I said, most of the unsupervised embedding methods, manifold learning methods, have this local fitting in their mind, most of them. So this is early exaggeration. Now there's also a paper which says that we can have general degrees of freedom in t-SNE. Do you remember we used Cauchy distribution, and as I told you that we can have a Cauchy distribution for embedding space in t-SNE, and we can call that even Cauchy SNE. But the student-t distribution in general is this. This formula is this. This is the PDF, probability density function for t-SNE, for a student-t distribution. And if we use it in softmax form, so this is a constant, let's drop it and take this part and use it in softmax form, we will have equation 34. You can see this. We are summing over all cases. And delta here is the degree of freedom. So we can still have this Gaussian distribution in the input space, but have this student-t distribution in the embedding space. And this is also t-SNE with general degrees of freedom. For determining the degrees of freedom, we can do different things. For example, we can set it to be a fixed number. For example, the original t-SNE or Cauchy SNE used delta to be 1. We can have delta to be h minus 1. Recall that h was the dimensionality of the embedding space. Why? This is the reason. So consider a circle, a sphere. What is the volume of what is the surface of a circle? It's p r squared. What is the volume of a sphere? It is this. So we can have volume of hyperspheres, and we can see that the volumes of hyperspheres are proportional to the exponential of h. Why? Because these are in powers. So when the relation is in the power. So by exponential I mean that. In equation 33 you can see that this term this degrees of freedom is also in the power, so its relation is also exponential. Therefore, we can say that the degrees of freedom and h are proportional. But so we can say delta is h plus some constant. What is this constant? Let's find it. The special case, usually when we use original t-SNE, most of the plots of t-SNE were in two-dimensional. So when delta was 1, when it was Cauchy SNE or original t-SNE, we plotted for two-dimensional embedding space. So let's take delta to be h minus 1. We can also update another thing. We can update both variables delta and y. So we can find embedding points as well as the degrees of freedom by restricted Boltzmann machine or backpropagation. So restricted Boltzmann machine is just a kind of neural network, but it says it uses the concept of energy in physics in order to find the weights. And Boltzmann machine, when we have nodes here and we come from these nodes to the next layer, this is restricted Boltzmann machine. But if we go back from the next layer to the first layer, this is Boltzmann machine. So if we only go from one layer to the next layer, and will not come back, this is restricted Boltzmann machine. This needs another lecture in order to explain restricted Boltzmann machine. But I can say to you that if you want to read more about it, you can search about restricted Boltzmann machine and deep belief networks. Using that or backpropagation, we can find both variables delta and yi in order to find that in loss function. We can also use alternating optimization approach, alternate between finding degrees of freedom and embeddings. So in alternating optimization problem, we iterate in each iteration. First we update delta using gradient descent, for example, then we update the embeddings. Then using the updated embeddings, we update delta again. Then using the updated delta, we find the embeddings, and we do it until convergence. This is alternating optimization approach. And we can have the cost function again. And if we, in this case, if we take this is the gradient of the cost function for the general degrees of freedom. For proof, you can see our tutorial paper. Also, if we want to use the alternative optimization approach, recall that we cannot use the ordinary gradient descent. Why? Because the degrees of freedom is an integer, so it's a discrete optimization problem. One heuristic way to solve this is that to use projected gradient descent, where when we project the gradient direction onto the direction that we want to go, and we'll go along to the sign of gradient in the gradient descent optimization. So this is what we can do. This is one approach. We can use different approaches for this discrete optimization. And another thing, we also use simple gradient descent for updating the embeddings, and we can iterate through these in alternative optimization approach. So we show here some examples. For example, here these are the embeddings of training data. These are the embeddings of out of sample or test data. In this lecture we have not covered out of sample embedding by SNE and t-SNE, but you can read our tutorial for out of sample embedding. Here in first column it is SNE. This is symmetric SNE. Symmetric SNE. This is t-SNE, original t-SNE or Cauchy SNE. This is the generalized the t-SNE with general degrees of freedom. And this is another example from the t-SNE paper. You can see that it has separated the classes of MNIST very well, very well. It's great. It was one of the breakthroughs in data visualizations in machine learning. And you can see that. Why do we have these spaces? Do you know what has caused the gaps between these classes? This was because of early exaggeration. And so in early, if you do that, you say that at first I want the points to the similar points to be close to each other, because if you don't do early exaggerations, these clouds of points will not become small, they will be larger. So the clouds of classes will be confused to each other. But if you do early exaggeration, the clouds, the intra-class variances become small, so the classes separate better. And then in later iterations, you care about the gaps. So you say, now that in the initial iterations, they have the similar points have become close to each other, now let's move these the classes away from each other. This is what t-SNE does. There is a tutorial paper that we have, a stochastic neighbor embedding with Gaussian and Student-t distributions. You can read that. There's also a good tutorial YouTube video by Professor Ghodsi at University of Waterloo. These are the references. This is the SNE paper, the original SNE paper. This is our tutorial paper. This is the t-SNE. Yes, this is the t-SNE with general degrees of freedom. This is the paper for t-SNE with general degrees of freedom. This is the paper for alternating optimization approach, and this is the original t-SNE paper or Kashi SNE. Okay, I hope this was helpful, and have fun.